Today we are talking about normal distribution. Okay, you're going to learn how to find probabilities that are distributed for continuous random variables. So binomial distribution was used with discrete variables, okay, such as defective lamps or number of shots or batteries. Things like that. That's binomial distribution because you'll have a fixed number. The probability is the same across the board, no matter how many times you perform this event. And then that's binomial distribution. Normal distribution, though, is for continuous variables. So those are variables that can be measured, such as height or time or weight. So normal distribution is used for those types of variables. Now, normal distribution, like I said, is for continuous random variables. If a random variable x has a normal distribution with a mean mu, that's the symbol for mean, and a standard deviation of sigma, it is written like what you see here. Remember when we did binomial distribution, it looked very similar? Well, there's another one for normal distribution. You'll know the difference because instead of a B, there's an N. N stands for normal distribution. The first number represents the mean of the distribution. The second number represents the variance. Now remember, variance is standard deviation squared. So that's why you see the symbol there. So if you're given a problem and it says this, then that means for this normal distribution, because of the N, the mean is 3. And then the standard deviation, it's not 9, it would be what? It would be, this breaks down to 3 squared, and so standard deviation would equal 3. Okay, so that second number is not the standard deviation, it is the variance, so don't get that confused. To refresh your memory about these two terms, mean and standard deviation, back when we did descriptive statistics, mean, it is the central point of the distribution. So again, it's the average, it's the middle. And a standard deviation describes the spread of the distribution. The smaller the standard deviation, the less it's spread out. Like the data that you collected is not as spread out across a range of numbers. These are called the parameters of the distribution. And again, the larger the standard deviation, the wider the curve, the smaller the standard deviation, the smaller the curve. And that's what you see here, okay? Mine has colors, yours necessarily does not. But again, no matter the values of the mean and standard deviation, the total area underneath the curve is always equal to 1 or 100%, okay? So 100% of the data that you've collected will be represented underneath that curve. So one normal distribution curve, which looks like a bell curve, is 100% of your data. This diagram also shows you a standard normal distribution curve where the mean is 0, and then a few other ones where the mean is, something other than 0, like the green one, the mean is -2. The other ones, the mean is 0, but different standard deviations. The blue line shows a small standard deviation of, a small variance of 0.2. So then the standard deviation would be the square root of that. That's why it's super skinny. It's not that spread out. But then look at the yellow one. The yellow one is a lot wider. Why? Because the standard deviation is larger. The larger the standard deviation, the wider it is. Okay? Now, will you have to draw a skinny normal distribution curve or a wider normal? No, you won't have to worry about that, but it's good to recognize which is which. Smaller standard deviations, skinnier curves. Wider standard deviation, larger standard deviation, wider curves.
What does it mean by area? It's always the same in equations.
That means that doesn't matter if it's a skinny normal distribution curve or wider. There's still 100% of your data that lies underneath that curve. So all of this represents 100% of the data that's collected for that particular problem. Kind of like what a Venn diagram is, like you have 100% of your stuff within that Venn diagram.
Oh, because what is outside is exception.
Right, outside of that box, anything here does not go to that 100%, but anything inside the box goes towards. Let's kind of talk about some notation differences. You have a normal distribution curve, which is representative with an X, but a standard normal distribution is where the mean is 0 and the standard deviation is 1. That is standard. That does not change for a standard normal distribution curve. The random variable that's used for a standard normal distribution curve is called Z, because it uses the Z values to describe the number of standard deviations any value is away from the mean. Now that may sound like a lot, but essentially, again, it represents the number of standard deviations that go away from the mean. So the notation for a standard normal distribution is what you see here, very similar to a normal distribution curve. But since this is a standard normal distribution curve, you use Z instead of X. Your mean is 0 and your standard deviation is 1. We use our calculator to determine the area underneath a normal distribution curve, AKA the probability of a particular value occurring, okay? For the next couple of examples, we're gonna just look at just purely numbers, but after we get through like the basis of how to use the different formulas, then we'll apply them to word problems. And so you'll see how like it applies to like an actual continuous variable versus just random numbers. Okay, so just kind of stay with me for right now. So it says, given that Z implies N 0, 1. That notation there tells you that you have a standard normal distribution curve. A standard normal distribution curve where your mean, which is in the middle of your distribution, is 0. How do I know that? Because remember, it always goes mean, standard deviation squared.
Which is variance, right?
Which is variance.
Okay.
Mhm. So essentially for part A, which again is going to be done in green, says to find the probability that Z is greater than -2, but less than 1. Well, if I look at this normal distribution curve where the mean is 0, -2 is to the left of 0, right? And +1 is to the right of 0, right? Essentially what I'm looking for is I'm trying to figure out, okay, out of that 100% that lies underneath my normal distribution curve, how much is that out of that entire curve? I'm trying to find that probability. I go to my calculator. So follow along with me on your calculator because you'll be pressing these buttons several times today. This is a normal distribution. So you want to go to second vars. Why second vars? Because there's a blue distra on top that stands for distribution. Second vars. It takes you to this list here. Number 1 says normal PDF. Number 2 stands for normal CDF. PDF represents a probability density function, the distribution function, and then C represents a cumulative. We're dealing with a continuous variable, so that is cumulative. It's going over a particular range of values. So we're going to use CDF. We always use normal CDF because we're finding a range from -2 to +1. So we click enter. Everyone's screen should say this, yes? Wonderful. It says lower, upper, mean, and standard deviation. Well, lower basically means out of the region that you're trying to find the probability of, what is the lowest limit? Or what's the lower limit of the shaded region? -2. So we're going to type in -2 here. Then it says upper. What's the upper region of the shaded area? 1. Our mean is 0, because that's what it was from the beginning, and our standard deviation is 1, so I don't have to worry about changing that. I go to paste. I like paste because you can look at it one more time, make sure you typed in all your numbers correctly, and then you click enter. That is the probability that Z is in between -2 and +1. So essentially roughly like 81.9% of the curve lies in between, or underneath the curve lies in between -2 and 1. But it's probability, so we write it as a decimal. Okay, what is the message on the error? That's on the top. What does it say? Okay, let's see. Now let's look at B. B, which I'm going to do in orange, says the probability that Z is less than 1. So when I look at my normal distribution curve, where my mean, which is in the middle, is 0, it says that Z has to be less than 1. Well, 1 is to the right of the mean, and less than, does that mean I'm going to shade to the left, or am I going to shade to the right to represent less than?
To the left.
To the left. And drawing these normal distribution curves and showing your shading is the work that goes behind this. Not what you type into your calculator, not that normal CDF in the parentheses. That's calculator notation. The drawing of the normal distribution curve is how you get your actual method points. So to find the probability, I go back to my calculator. How do I get to normal CDF again?
Vars.
Second vars, and it's always option 2. Now this one's a little bit different because for lower bound, technically this curve goes on and on and on forever. Like the x-axis essentially is like an asymptote. So the normal distribution curve is going to get very close but never actually touch it, which means that the lowest bound here is a really, really, really small number.
Mm-hmm.
If you think about a number line, what number is all the way to the left?
Infinity?
Negative
Infinity?
negative infinity, right? But there's no infinity feature here in the calculator. So what you type in is a really, really, really small number, okay? Or a large negative number. The number that's good to use is basically -9 times 10 to the 99th power. That's a -9 and a whole lot of zeros. So you go -9 times 10 to the 99th power. Okay,
I have a question.
yes,
Why don't they put the infinity button in here?
because technically infinity is not a number, it's not a numeric value.
Oh, okay.
So us using this is essentially representing a really, 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 really small number, but there's technically a smaller number beyond that. This actually allows the calculator can calculate with a number this small.
Mhm.
If you try to go any smaller, it's going to give you an error message.
I see.
Okay.
I have a question too.
Yeah.
Can we use like E?
You can use E. So check this out. I know you guys have seen this as well in your calculator, like when you're doing things and you get that E at the end. That E is technically right here. If I go -9, if I press the second button and the comma button, it pops up an E. That is scientific. That's the calculator's version of scientific notation. So instead of doing times 10 raised to, putting the E is technically that. So then I can just do 99 and it's the same result.
Mm.
So you can either actually type it out all the way, or you can do second comma 99. My upper limit is 1 because that's the upper bound of my shaded region. Mean is still 0, standard deviation is still 1. I paste, double check, lower, upper, mean, standard deviation, and that's my probability. Is 0.841.
Mhm.
This is how you find normal distributions. Let's do the next one. Doing it in purple. Mean is still 0, but this time I'm doing Z is greater than -1.5. -1.5, is that to the left of the mean or the right of the mean?
On the left.
Left. And when I shade, am I shading to the left of that value or the right?
To the right.
Because it's greater. And again, drawing these normal distribution curves suffices for your work. I go back to second bars. Second bars, option 2. What's my lower bound this time?
Negative 1.5.
Mhm. What's my upper?
Infinity.
How do I represent a really large number?
9 second, comma 99.
9 second comma 99. So remember that E represents the scientific notation. Mean is still 0, standard deviation is still 1. That's nice when you have like several problems that use the same mean and standard deviation. You only got to change the upper and lower bounds. That's it. So that'll be 0.933. Let's keep going. 0. What is 0?
Or me.
0 was our mean. So when we do this, I was going to do that. So when we do this, and it says less than, that means we're going to the left or the right of the mean.
Left.
Means we're going to the left. So we're shading all of this. What's my lower bound?
Negative.
Negative infinity, so that's negative 9 e to the 99. What's my upper?
2.
Mean and standard deviation stay the same. So that's essentially 50%, 0.5. The mean is 50% of your normal distribution curve, always. Last but not least, you have these bars around Z. What do those bars mean?
Absolute value.
Absolute value. What is absolute value?
It's the natural number.
Essentially, yeah. But it is the natural value of that number. But what does it represent?
I don't know.
It's how far it is away from 0. If you think back to absolute value equations, remember you always used to do a positive one and a negative one? That's because the distance from 0 to either negative 0.8 or positive 0.8 is the same distance. So when you see the symbol, it's not just 0.0, it's not just 0.8, okay? It's actually including negative 0.8 as well, because the distance from negative 0.8 is the exact same if I was going to point from 0.8. But the shading, since it says it's going to be greater, recall absolute value inequalities. One greater, the other one you had to switch the sign and change it. So you're trying to find this here and this here. You're trying to find both of those probabilities. You add them up and you get your answer. Okay. So how do I do that? Second bars, normal CDF. Since I already have negative 9e to the 99, I'll do the left side. Negative 0.8 is going to be my upper limit. And I'm going to paste. That's that value. Now, real quick, 0 is the mean. It splits my normal distribution curve into 50% and 50%. So the area that's to the left of negative 0.8 is going to be the exact area it is greater than 0.8. So all I need to do is double this to actually get my full probability. If you don't trust it, you can always do the normal distribution using 0.8 as your lower and then positive infinity as your upper, and you'll see, you'll get the same value that you got when you did negative 0.8. So my answer is going to be 0.424. Yes.
Why did we double it again?
Because a normal distribution curve is symmetric about the mean. So since in part D, we found the probability of it being less than 0, the mean, and we found it to be 50%, that means the mean splits it in half, which means that everything is symmetrical about the mean. So 0.8 and negative 0.8 are the same distance away from the mean, which means that those two areas, those two shaded areas that are to the left of negative 0.8 and to the right of positive 0.8 are going to be equal. Because again, it's symmetric about the mean. So if you're the same distance away from the mean, then the areas that are to the opposite ends are going to be the same as well. So we can get that answer by doubling one probability, or we can find the two. This one was greater than 0.8. This one was less than negative 0.8, and just add them together, but we get the same value. So we get the same value as we did before. So this is how you find normal distribution. This is, of course, for a standard normal distribution. So very few real life variables are going to model a standard normal distribution. Okay, they're going to follow a regular normal distribution. But knowing how to transfer from a normal distribution to a standard normal distribution is helpful. And you'll see some examples of why this formula that I've circled in that red, darker red color is important. It's Z equals X minus mean over standard deviation. Z stands for your Z score. It's essentially that value on the x-axis when the mean is 0 and the standard deviation is 1. The capital X represents the actual numerical value of the real life variable. Mean, of course, is your mean, and sigma is your standard deviation. Okay. So again, this is how you convert from a normal distribution to a standard normal distribution. Okay. Now, just follow me as I walk you through this example. I know you're probably going to be like, well, can I just do it the other way? Yes, but I'm just showing you how it works. It says the normal variable or the random variable X implies a normal distribution where the mean is 10 and the variance is 2 squared. So that means standard deviation is 2. So mean is 10, standard deviation is 2. It's asking me to find the probability of 9.1 to 10.3. Now, you can do this using normal CDF like we've been doing. My lower limit would be 9.1. My upper limit would be 10.3. My mean, though, would be 10, and my standard deviation would be 2. Okay? Like I can literally type that in and get my answer. Yes, there is nothing wrong with doing it this way. Okay? To be honest, I'm always going to encourage you to do it this way. Okay? Because if you have all your information, if you have your mean, if you have your standard deviation, do that and get your answer. That's the probability. However, there might be a situation where you can't just use the information that you have because maybe you're missing something. That's when that other formula is going to come in handy. Okay, if you're ever missing a piece of information, this formula is very helpful. But let me show you what I can do with this formula. I can turn 9.1 and 10.3 into values that are on your standard normal distribution curve. That's where your mean is 0 and your standard deviation is equal to 1. How do I do that? Well, I take this value and I plug it in for X. I subtract the mean and divide by 2. So 9.1 minus 10 divided by 2 is negative 0.45. Negative 0.45 corresponds to 9.1 on a normal distribution curve. Okay. I can do the same thing for 10.3. Make sure you stay with me. I'm showing you how to use this formula to convert from a normal distribution to a standard normal. This skill is going to be helpful later on down the line. That corresponds to 1 or 0.15. I'm still finding the area in between. So I can do second bars, normal CDF. Oops. My lower limit is negative 0.45. My upper limit is 0.15. Standard deviation is 0. I mean, mean is 0. Standard deviation is 1. And you see I get the same value I got before. So whether you convert to a standard normal or you leave it as a normal distribution, you'll get the same value.
Wait,
No.
so, oh, you can.
Okay. So now again, you do not have to convert a normal distribution into a standard normal distribution like what I did here. If you have all of your information, you can do it the normal way. If you have your mean, your standard deviation, and your X value, you can find the probability. But if anything is ever missing, you need to use this formula. Okay? So again, you do not always have to convert to standard normal distribution, but it's important to know how to go about that standardization. This is your normal distribution curve. You've seen it enough times already to know that it is a bell curve. But what you probably haven't seen is that this is how it breaks down. You have your mean in the middle. We know that. We also know that the mean splits the area underneath the curve into 50% on both sides. It splits it straight down the middle. It's symmetrical, 50-50. Now, you can have up to 3 standard, well, actually you can have more than 3, but for the sake of this class, you'll go up to 3 standard deviations on both sides of the mean, okay? Now, 1 standard deviation, 2 standard deviations, 3 standard deviations. Why is this important? Well, let's say that you happen to have a non-calculator question that deals with normal distribution, okay? And they happen to give you the values that actually lie on the standard deviation. From 1 standard deviation to 1 standard deviation, that makes up 68% of your data. So from 1 standard deviation to the left of the mean to 1 standard deviation to the right of the mean, that is 68% of your data. From 2 standard deviations to 2 standard deviations, that is 95% of your data. And then from 3 standard deviations to 3 standard deviations, that is 99.7%. Now, yes, these are approximations, and these are the approximations that you'll want to use if you ever have a normal distribution problem that is a non-calculator. Okay, so this is how the breakdown of a normal distribution curve is. Whatever the mean is, say it's 50, and then the standard deviation is 5, then this value will be 55, this value will be 60, this value will be 65, because you just keep adding a standard deviation. You will subtract, this will be 45, this will be 40, this will be 35. How do you use this again? Let's say they want you to find the probability that someone's age is between 45 years old and 55 years old. Well, that lies on your standard deviation, so you can say about 68% lies in between 45 and 55 years old. So these you'll need to remember. So like I said, that breakdown, 68, 95, 99.7. You'll need to know those in case you happen to have a problem without a calculator. Like this one. It says let X be normally distributed with a mean of 75 and a standard deviation of 5. Draw your normal distribution curve to represent this information. Well, I need an X-axis and I need a normal distribution curve. You try to draw the smoothest curve you can. You want to make sure that it's asymptotic to the axis that you draw. Smack dab in the middle is your what again? Your mean, which is 75. Now it says a standard deviation of 5. That means 3 standard deviations to the left, 3 standard deviations to the right. You'll need to either add 5 or subtract 5. And that's how you draw your normal distribution curve. So if I go to the left of the mean, what's this value?
80,
80. The next one,
85,
and the next one after that,
90,
90. Let's go to the left of the mean. What's this one?
70,
Keep going.
65,
And then
and 60.
there you go. And just like with any graph or diagram you draw, you want to make sure you label this one does not have a value for X. So then you just put X.
I'm missing whatever note we were supposed to.
So then it says, given that the probability that X is less than 65 is equal to the probability that X is greater than A. Find the value of A. Well, look at 65. 65 actually lies on one of our standard deviations. It's on our second one. So remember, this is mean. This is mean minus 1 standard deviation. This is mean minus 2 standard deviations. So the probability that X is less than that value is going to equal the same probability as X being greater than some similar value. What's that value going to be? What is the value of A? What's the value of A? 65 is on what standard deviation? The second, which means that whatever probability is less than that value is going to be the exact same as the probability of X being greater than some other value.
85.
It's going to be 85, because isn't 85 your mean plus 2 standard deviations? It is. So because 85 is your mean plus 2 standard deviations, those two values are symmetric. Okay? Because the mean again separates your data into 50% to the left, 50% to the right. So if 65 and everything less than 65 is 2 standard deviations, then its similar counterpart on the other side of the mean is going to have that same probability. So A is equal to 85.
I really don't understand. Maybe the question.
Now it says, given that X, or given the probability that 65 is less than X, which is less than A, the same A from part B, is 0.954. Find the probability that X is greater than A. That A is the same value of A we found in part B. So essentially this is saying between 65 and 85, the probability is 0.954. That's what that says. So everything in between my 2 standard deviations is 0.954. Before anybody says anything, remember that 95%, that was an approximation. Okay? It's an approximation. So this right here represents 0.954. It's now asking you to find the probability that X is greater than 85. So it's asking you to find this part right here. What is this probability? That's what the question is asking you to find. How could I find that probability knowing about 2 standard deviations, knowing that the mean splits my curve, my probability in half? How can I find the probability of that purple part that I've boxed in black? That is definitely one way to do it. I can take 1. I can minus it for 0.954. And then that value I can divide by 2. Because how much is underneath the normal distribution curve?
100%.
100%, or a probability of 1. So if I do 1 minus the probability I know, which is in yellow, then divided by 2, because remember, these are equal. The green and the purple are equal probabilities because they were equally spaced away from the mean. So by dividing by 2, I will find just 1. Now this is non-calculator, so I might have to go a little old school here and do some subtraction. Borrow, borrow, borrow. I don't know how you learn how to do it, but this is how I learned how to do it. So 1 minus 0.954 is 0.046. I need to divide that by 2 to get my answer to part C. What's 0.046 divided by 2?
0.023.
And then that would be the probability that X is greater than 85. So again, A was the value on the axes that corresponded to part B. And then part C, we're actually finding the probability that X was greater than 85. And that was 0.023. Let's look at a real world situation. It says eggs laid by a chicken are known to have a mass normally distributed with a mean of 55 grams and a standard deviation of 2.5 grams. What's the probability that an egg weighs more than 59 grams, smaller than 53 grams, and then between 52 and 54? This one clearly is going to be a calculator problem. How do I know this? Well, if I look at the mean of 55 and a standard deviation of 2.5. Well, if I add 2.5 to 55, what do I get? And then if I add 2.5 to 57.5, what do I get? And 59 does not lie on, it's not one of those. So it doesn't lie on a standard deviation. It lies in between two of them. So this one I'll have to use my calculator to do. More than 59. Am I shading to the left of 59 or the right of 59? To the right. Okay, so this is going to be part A. And what I've drawn here, normal distribution curve where 59 is located and the proper shading, this is my work. So you're going to be drawing normal distribution curves to justify your answer. Go into my calculator. What do I press?
Second vars.
Second vars. I go down to option
2.
2. What's my lower limit? Nope, not 55. 59. So I'm trying to find the probability that it weighs more than 59. So that was that red, and I shaded to the right. So 59 is my lower. What's my upper? Infinity. I already got it there. 9E, 99. What's my mean? And my standard deviation. So I paste, double check, and that's the probability that if you select an egg from this particular situation, it's going to weigh more than 59 grams. So very small. How do I round it to 3 significant figures?
0.0548.
Very good. You start with your non-zero number and count. Okay, I want you guys to try B and C. Do B and C on your own. So the next one says an egg is smaller than 53. Okay, so here, again, another normal distribution curve, mean in the middle. Always include the mean. So then that way, when you draw your line either to the left or the right of the mean, that's like always one of those indications that you drew it to the correct side. 53 is on this side. Am I shading left or right? Okay, I'm going to go and use normal CDF again. What's my lower limit? Negative infinity. Upper. And my mean and standard deviation stay the same, right?
Yes,
Did you guys get this?
yes.
So 0.212. Lastly, for C, this time, again, my mean is 55. I have between 52 and 54. Both of those are to the left of the mean. And between means I'm looking for this part right here. What's my upper and lower?
If you choose the lower.
Mean and standard deviation are the same.
Yes.
Okay, so I gotta change that to 55 and 2.5. I know why I went back to that, because I accidentally clicked something earlier. Did you guys get this?
Yes.
How do you round that to 3 significant figures?
0.230.
With the 0. There you go. That's how you find probabilities. Normal CDF allows you to find the probability underneath a curve to model these different situations. This one here. Machine produces bolts with diameters distributed normally with a mean of 4 and a standard deviation of 0.25. Bolts are measured accurately, and any which are smaller than 3.5 or bigger than 4.5 are rejected. Out of a batch of 500 bolts, how many would be acceptable? This mixes what we're talking about today and currently with an older concept of expectation, expected value. Okay, if I have 500 bolts and I'm trying to figure out how many of those bolts will be acceptable, I need to take that number and multiply it by the probability. That is N times P. That is expected value. Okay. The only thing I don't know is the probability of what would be acceptable. Okay. But I do know that anything smaller than 3.5 and anything bigger than 4.5 is going to be rejected. So it's acceptable if it's what?
In between those two?
In between those two. So in between 3.5 and 4.5 is going to be acceptable. The mean is at 4. So anything in between here is acceptable. I need to find that probability. This represents P. I'm then going to multiply that by 500, my N, to figure out the number of bolts that are going to be acceptable out of a batch of 500. So I go back to VARs, second VARs, normal CDF, in between. So that's 3.5 to 4.5. I have a mean of 4 and a standard deviation of 0.25. That's my probability. But I multiply that by 500 to find my number of expected bolts. So I multiply by 500. How many bolts do I get?
477.
477. So it mixes a little bit of expected value with some normal distribution. That's common. That's very common. Now with normal distribution, I don't know what it is, the students tend to forget what I'm about to introduce now and when to use what. We use normal CDF to find what? Like anytime I use normal CDF, I was finding a what?
Continuous?
Well, it's for continuous variables, but the value of like 0.954 was a probability. Normal CDF finds a probability. The probability of an egg being more than 59 grams. The probability of X being greater than 85. The probability of an event happening. You use normal CDF. But when you know the probability already, but you don't know the X value on the axes that's associated with it, you use what's called inverse normal distribution. So when you're looking for an X value, you use inverse normal distribution. This is when you're given the probability but not that value that corresponds on the normal distribution graph, okay? So essentially, for example, it says a company fills cartons of juice with a nominal value of 150 milliliters, okay? 5% of the cartons are rejected for containing too little bit of juice, okay? So 5% of my containers are rejected if they contain too little bit of juice. The owner of the company may wish to find that cutoff point, the minimum volume of the carton that's going to cause us to reject it because it has too little juice. We don't know what that value is. We don't know how many milliliters that is when we start to reject it because it has too little bit of juice. You use inverse normal to find this out. Inverse norm finds the X value on the normal distribution curve. Normal CDF finds the probability. Okay? Do I actually use that example? Yes. So I did skip over one example to give it back to the juice example, but let's do this. It's rejected for containing too little bit of juice. I know that when it's 5% or less, I reject. So I need to figure out that value. It says that my mean is 150 and my standard deviation is 5. Where do I go to get inverse norm? I go back to second vars. This time I go to option 3, inverse norm. Does anybody's calculator not look like this when you go to second vars, option 3? Does everybody have a tail? That's the main question. Okay, so if yours doesn't have a tail, the newer calculators do, the older ones don't. Your tail they're talking about is referring to the shaded region. Unfortunately, if you don't have the tail option, your shaded region is always to the left. So even if the problem has the shaded region to the right, your calculator can only do the area to the left. Okay, so this is what we're going to do. Luckily enough, this problem is to the left. We do have a problem where it's the other way. So area represents the probability. Probability was it was 5%. So convert that to a probability. What would that be?
0.05.
0.05. I type that in for my area. Area means the probability of the shaded region. The mean was 150. The standard deviation is 5. Now, for those who actually have this next line tail, you have to tell your calculator, okay, is my shaded region to the left? Is my shaded region in between two values, center, or is it shaded to the right? Where's my shading?
To the left.
To the left. So I want to make sure left is highlighted. For those who don't have the tail, you don't have to worry about doing this because the area is already shaded to the left. I go down to paste and click enter. That is the value of X. That's the number of milliliters that when it goes below that value, that's when they got to reject it because it has too little juice. How many milliliters is that?
141.
3 significant figures.
2.
142.
So we can round it.
Well, we want to do 3 significant figures regardless. Still. So that second one, that 7 causes us to round that 1 up. So at 142 milliliters, anything less than that, they have to reject because that's too little bit of juice. And we find that value by doing inverse norm. Let's look. Man, okay, it's fine. Let's look at this one. You may be asked to find the mean or standard deviation or both instead. It says a sack of potatoes with a mean weight of 5 kilograms are packed into an automatic loader. In a test, it was found that 10% of bags were over 5.2 kilograms. It was over 5.2 kilograms. Use this information to find the standard deviation of this process. So what does that mean? You had a mean weight of 5 kilograms. They found out that 10% of the bags were over 5.2. Here's 5.2 kilograms. If I go over, is that to the left of 5.2 or to the right of 5.2?
Right.
Right, because I go over. And that probability is 10%. So this here is telling me, okay, well, I already know my X value of 5.2. I know the probability is 10%, that's greater. The only thing I don't know is my standard deviation. That is where this formula, Z equals X minus the mean over standard deviation comes into play. Because this formula is the only thing that connects the mean and the X value together with the standard deviation. So let's plug in what I have. I know that X is 5.2 because that's the value that's associated with the probability. My mean is 5. My standard deviation is unknown. And some of y'all may be thinking, well, Z is unknown as well. It's just unknown right now because we haven't found it.
What is Z?
Z represents the Z-score. That is associated with the standard normal distribution curve where the mean is 0 and the standard deviation of 1. 5.2 corresponds to a value on your standard normal curve that will help you find the standard deviation for this particular problem in the orange. So what do? How do you find this out? You need to figure out what is the Z value that's associated with 10% being greater. Why 10%? Because it was 10% here. So to find the Z value, to find this unknown value on my X-axis, I have to do inverse norm. I have to do inverse norm because again, I know a probability and I'm looking for an X value. Technically I'm looking for a Z value, but same thing. So I go to second vars, option 3. Now, for you and for the ones who don't have the tail feature, you cannot type in 0.10. Because remember, your calculator automatically defaults to a left tail, the area that's shaded to the left. Right now, I don't have area shaded to the left, I have area shaded to the right. But what is this area that's to the left here? How much of the curve is that?
90%.
90%. So for you, and for any of the ones who do not have the tail feature, you have to type in 0.90. In other words, the complement of the area that's shaded to the right. You'll type in your mean of 0, not 5, standard deviation of 1. Because we are looking for the value of Z that we're going to plug into this formula to find my standard deviation. Now, I'm doing this way first, because this is for those people who do not have the tail feature, because it automatically does the left. Click enter, this should be your value. For those whose calculators are like mine, when I go to inverse norm, I can type in 10%. I'll have a mean of 0, a standard deviation of 1. I just had to tell my calculator that this is the right tail, because that's actually where the shaded region was for us. And I get the same value. Okay. So 1.28155, so on and so forth, represents the Z value that corresponds to the 10% being greater than some value that I can plug in right here to complete my equation for me to solve for my standard deviation. So to solve, I multiply both sides by my standard deviation. I don't want to round because that's going to throw it off. And then I'll just end up dividing both sides by that long decimal. So that's what I type into my calculator. 5.2 minus 5 divided by this long decimal that I just had. And that is my standard deviation. So a lot of things happened in this problem. Let's recap. First off, I did not have my standard deviation, which means I needed to use that Z formula to find it. To find the value of Z, I had to essentially find the corresponding Z-score on a standard normal distribution. I use my standard normal distribution because the mean is automatically 0 and the standard deviation is automatically 1. That helps me find the value of Z that gets plugged into the formula so I can solve for my standard deviation. You use inverse norm to find that Z-score. Inverse norm, for those who do not have the tail feature, always have to use the probability that's to the left of that value. Otherwise, you're not going to get the correct Z-score value. Anybody who has the tail feature just has to let the calculator know we're talking about area to the left or to the right. The manufacturer does not know the mean nor the standard deviation of the diameter of a ball bearing she is producing. So she knows no mean, no standard deviation. However, the machine that rejects balls says that it will reject all ball bearings that are larger than 2.4 centimeters and those that are under 1.8 centimeters. So what does that look like? If it's over 2.4, she rejects. And if it's under 1.8, she rejects. It's found that 8% of the ball bearings are rejected if it's too small, and 5.5 are rejected if it's too large. Everybody understand how I got that drawing and those probabilities? So now you just have to find the mean and the standard deviation. So since I don't know either, but I do know 2 X values and 2 different probabilities, I'm going to create 2 Z-score equations. One that represents when X is 1.8, and then the other when X represents 2.4. Okay, so I'll say that again. I'll create one equation when X is 1.8 and a second equation when X is 2.4. The last piece I'm missing before I can actually start algebraically solving for my mean and my standard deviation is my Z-score for each. Remember, we find Z-scores by using inverse norm. So I go second vars, option 3. Now I need probability. Let's do 1.8 first. 1.8, the area underneath the curve was 8%. What's that as a decimal?
0.08.
My mean is 0, my standard deviation is 1. The tail, is it left, center, or right?
Look,
It's left, because that's where the shading is. And remember, those who do not have the tail features automatically to the left. So I don't have to do any subtracting here. I can just use 0.8 and paste. That's my Z-score. That's what's going to go on the left side of my first equation. Do not round it. The more you round, the further you're going to be away from your mean. So give me all them decimals. It's negative 1.4. Perfect. Now let's find my Z-score for 2.4. Now, for those who do not have the tail feature, you're not going to be able to plug in 0.055. You'll have to do the complement. So remember, your calculator can only do area that's to the left of that X value. Okay, so first, before you go to inverse norm, do 1 minus 0.055. And then whatever that value is, that's what you plug in for area. Okay. But for me, I can just do 0.055 and I just tell my calculator to do the right tail.
I get it.
So when I go to paste it, that's my Z-score that goes in. Now, Howard, did you use the other one and then kept the mean 0 and standard deviation 1? Did you get that value? Okay. So that's 1.59. Read them off.
8193139.
So you have two different equations with two different variables. You're going to use system of equation to find your mean and standard deviation. All right. So I'm going to multiply both sides by my standard deviation. On both equations. And if you're like, oh my goodness, this is a lot. But look, my mean has the same coefficient. Y'all remember elimination?
Yes.
As long as they have the same coefficient, all I gotta do is just change the sign, right?
Mhm.
So if I make this bottom equation negative, like I multiply by -1, that allows my mean to cancel out. And then all I have to do is essentially combine my like terms, okay? It does kind of look like a lot. This is because you're kind of dealing with you're dealing with that long decimal first off. And then over here, I'm going to take this value and subtract this value. That's that value. So -3.003267 standard deviation equals -0.6. To find my standard deviation, I just divide both sides by that number. So my standard deviation is going to be what I get when I take -0.6 and divide it by -3.003267. And that's my standard deviation. When I round to 3 significant figures, I'll be 0.200. Then to find my mean, all I have to do is plug that value in and solve, okay? So I'm gonna plug it into the right equation. I'm gonna take that 1.59 number, multiply it by my standard deviation, and then I'm gonna subtract 2.4. Why? Well, I'm solving for my mean. If I plug in this value in for my standard deviation, I multiply it by this number, and then I will subtract 2.4 to get negative mean equals that negative number there.
Which is the positive.
And I want the positive version to actually find my mean. I know I went through this kind of fast because I was running out of time, but that's how we can find the mean and standard deviation. Two unknowns, but using the Z-score.